So if we talk about BFS of this graph, so BFS means we start from one node and first we traverse its neighbors like level order traversal. Then we go to their neighbors, then we go to their neighbors. It spreads like that. And in graph it is important, whenever we do BFS or DFS, we need one starting point because graph does not have concept of root. So let's say if we are starting with a 2 as our starting point, what will be the BFS here? From first we will take 2. Typically in BFS or level order we take Q. So we take 2, we put it into the Q, and then we start the loop. First node kept in the Q, and we start popping while Q is not empty. That's how we did in tree also, level order traversal, right? So now we take 2 out of the Q. Who are the neighbors of 2? Only 4. 2 is taken out, printed, its neighbor inserted in the Q. Now next thing that we do, Q is still not empty, we take 4 out. After taking 4 out, we print 4. Who are adjacent to 4? 0, 5 and 2. Because when we write that loop, we will reach to all 3. They are adjacent. So we go to 0 first. Let's say, because it depends on which node we are going to, it depends on how we have inserted in the linked list. Ultimately we are going on adjacency list. So from 4 we go to 0 and we check, is 0 visited or not visited earlier. Visited means has that been added to the queue or not. If 0 were added to the queue, we don't add again. If it is not added, we add it again. Now 0 is added. After that 4 has the next one, which is 2. Now we check, 2 should be marked visited because we added it for the first time. So 2 we don't add again. 5 we add it again. So this is the state of queue right now. So in BFS what we realize is, one thing we need is queue. Second thing we need is array, visited array. What will be the size of that array? Number of vertices that we have in the graph. So every time we have to make sure we are marking visited, not visited. In tree we did not use the concept of visited. Why?
Because you don't come to the node again, sir.
Yeah.
Once you go down the level.
Because in tree there is, between any two nodes there is only one path, right? From root, 2 children, from that child another 2 children. So we don't have the concept of duplication there. Here we can come again to anything. So here I think BFS that is marked, it is for this print graph. From 0 we go to 4, we go to 3. So if this is the print graph output, this is the BFS. Now you can code BFS using STLQ. So let's open our project that yesterday was created. Now what will be the function signature for BFS? Return type will be void because ultimately we are printing. Input parameters, it needs a graph. Okay, next. Starting vertex, from where we start the BFS. So BFS that we add here, okay, previously there is a function signature added. Let's modify that because this signature assumes we are starting with 0. So we add int v. So just add it to the old function signature that we have, BFS comma int v. So this is what we have to implement. And same way also add int v to DFS. So that is the next function we are going to write, int v. For q, there will be 2 things required, hash include q and using namespace std. and in BFS you will be writing queue of, what are we storing in the queue?
LL not star.
Should we store LL node star or integer will do? Because we said our graph is 0 to n only. Will int do? If we just put the vertex number, that should suffice for us. So we will go with queue of integers. Yeah, so we take a queue and we get started. You need a visited array also. So here we need to define visited array, which is data type of that will be bool, size of that will be g of nv. We can give variable name also as the dimension for array. So it will be later on if graph is 1000, 2000 vertices. So here we are taking visited of g of nv.
Sir, that is variable no sir.
Should take, wait, because at runtime this variable will have some value, either garbage or non-garbage, right? So at runtime, C runtime can figure out what is the value of that variable, that much allocation I have to do, because that allocation happens whenever we come into the function. When the stack frame has to be created, that time it has to be allocated. So by that time C will assume this variable will have some value. No, V is the start vertex. In BFS we are starting from vertex number 2 for traversal or not. So NV is total number of vertices in the graph, and this V is the starting vertex from where we are starting BFS. Of visited. Then there you will not be able to use G of NV. So ideally if we take global, unnecessarily we will have to go with the size of 1000, 2000. We have to take such size such a way that it is big enough to hold for any graph. This way if we go, then we are going specific as per graph. Now in this array we have to put false initially, because local variables are never initialized automatically. If this was a global array, by default false would have been there. In local we don't have 0 values. So how do we initialize? By writing a loop, going to every index, making that false. There is another way also to initialize an array.
Equal to in curly braces 0.
So you write
False.
visited equals to false. This, let's see,
Declaration only sir.
in declaration only here. Okay, so let's go with this. Variable size visited may not be initialized. That notation is allowed. Wait, that notation is also valid, but here let's put 0 and see, because when we put 0 it says it will initialize everything to 0.
Means that G of n is variable.
I think here it should be 7, then it will work. For variable sized array that will not work. So that notation is there, but if we know the array size in advance, it can be done. There is another way than this, which is useful for context kind of problems, and that is one line code. So there is a function in string.h which is called memset. Have you heard of that function? Memset. So memset goal is you just tell the starting point of the memory, where the memory starts, tell how much memory is there and what character you want to put in that memory. So we look at the signature of memset so that we can use it efficiently. Memset in C. So you should be aware there is a shorthand way also of initializing any given memory. Yeah, so if we come here, we see memset sets the first number bytes of blocks pointed by PTR to specified value, interpreted as unsigned char. So we are giving the pointer where the memory starts, what value we want to put, and how much is the total memory that we want to fill with zeros. Pointer to the block of memory to fill, value to be set, it is passed as int, because characters and integers are interchangeable. number of bytes to be set to the value. Pointer, same pointer is returned back, whatever we pass that is returned back, so we are not worried about taking the return value. So syntax will be here. If this was the array, it says in this string make first 6 characters as dashes, right? So here what do we do? Memset visited, that is our starting memory, false, false will ideally be 0, yeah, then g of nv, but g of nv is not the size of memory. I think last parameter is number of bytes, how many bytes of memory we have that we have to set. So how do I get the size of this array? Size of, this is one way, or second is g of nv into size of char or size of bool, sorry, right? Those many booleans, g of nv booleans, this is the size. So this way if we go, so this will be useful in other problems that we have done of integers. There also we can say set everything to 0 because it takes integer, internally it will figure out the character. Okay, so this is shorthand way. You now start with BFS, write the code. Okay, so if we go with that function graph BFS, yeah, so what we are saying in the beginning is visited array we took, we have set it to false, then we are saying in this graph, in this queue we will put push, it is push or push back, okay, there is a function push back also, okay, push, what do we push? V, after we push it, visited of V we mark as true, that is what has to be done. After that we say while q dot empty, it is while it is not empty, what we have to do, we have to continue with its children. Okay, first thing we should do is we should pop q dot pop, whatever we pushed we are getting it out, pop does not return anything, so we should take top front here, so you can directly go with %d space q dot front, okay, front we are putting and then we are popping. After that all the adjacent nodes of V should be inserted in the queue. So what we should do for that, for ll node star temp equals to head of, where is the head of this linked list, adjacency list of V, g of adj list of V, at that we are starting, it's like traversal we are writing, till t is not equal to null, t equals t ka next, right? What should we do with this t? Iska data we have to put in the queue, so we say q dot push t ka data, and here after pushing it we have to make sure this does not get pushed again, so we say visited of t of data is true. This is clear? So at every node we are inserting its adjacent nodes by writing a loop, because we don't know how many adjacent nodes it may have. And before pushing we should also check whatever we are pushing, it is not visited already, right? So we should check if visited of t of data is false, only then we should push, otherwise if we push it will be a duplicate entry. So these two things are important here to keep in mind, otherwise this algorithm is straightforward. So some people use recursion here. Someone use recursion? No. Vineet used recursion, Sanjay used recursion. How is your output coming? Not coming. So we will try that also and we will figure out why it is not coming properly. Ideally here recursion wasn't needed, but if you have thought recursively, good. We'll talk about that solution and we'll see if recursion is giving the right result or not. Okay, memset. For memset, which file to include? String.h. So string.h. LL node is not here. Std bool for boolean. Anything else? LL node no member date. Okay. Did I put date anywhere? Okay, here data. Okay, this error is coming in destroy. That is fine. Now earlier, if you remember, the signature was not having a vertex here, right? Because in graph the challenge is there is a graph possible. This is 1, this is 2, this is 0, this is 3. This is a graph, because it is not necessary that every node will be connected to another node. So this graph, we say it is disconnected graph. It has two components. 1, 2 is one component, connected component. 0, 3 is another connected component. Now if we do BFS of this, to print the complete graph, we have to first do BFS at 1, then we do a BFS at 0. Then only this BFS will complete. I guess that is why our BFS earlier did not have start vertex. So I'll remove that from here, so that whenever we do the traversal, we make an assumption we are starting with 0. So I come here, because our intention is to print the complete graph. So BFS. So what we will do here is, we will say we want to start this complete traversal by considering every node. First start with 0 and do a BFS. So all the nodes connected to 0 will be covered, and everything will be marked true also, right? Then we say start with 1 and do a BFS. When we start with 1, 1 will not be pushed itself, because 1 is already visited. So that's why we have to go to every node, because we don't know which node is disconnected. So that is the change that is required. So here we write another loop for I0, I less than g of nv, I plus plus. And here what we do, rather than v, we push I, and before pushing I, we also check if visited of I is false, only then push and proceed. Otherwise skip this node completely. So I am moving inside code into. So what we are doing, we will do a BFS with every such node which is not visited previously. So we start with 0, we do a complete BFS. Then we go to 1 and check. If 1 was not visited in BFS of 0, we do a BFS with 1 also. Right? So
But BFS will give only which is connected, no, sir. Only which is connected graph we need to generate BFS.
no, any graph you can do a BFS.
Means here we have to not connected components. 1 and 2, 0 and 3. Yes. So if you give 1, only 1 and 2 should get printed. 0 and 3 should not be.
They should be. I mean, it depends on what we are considering BFS to be. My assumption of BFS is, when we are doing a BFS of the graph, even if it has 1 component or 10 components, everything should come as an output. So if that is the assumption, then this is the BFS. If it is about do BFS only of a connected component, then previous function that we wrote, that was fine. You give the starting point, it will do the BFS of connected component will come out. So here assumption we have changed. We are saying this is BFS of entire graph starting with 0 to n. Okay, v was not declared, now v has to change everywhere. Adjacency list of I, it should be. Function is not, definition is not allowed. Okay, I missed closing of that. Okay, now it is fine. I go to main, say BFS of G, and go ahead and run it. So now it is coming 0, 3. So 6, 7, they are not connected components, so they are printed separately. Okay, Sanjay, your logic, recursive. What is that? So first these lines are equivalent, right? Okay, so this we are saying this will be BFS 2. Yeah, then what did you do? If Q is first you have to push. Okay, Q dot push. So here what should I do? Or before pushing, you have started with the initial vertex, right? Fine, we will go with that for now. Int v. So you are saying push v.
Before that we should check if it is visited.
Fair.
Visited, then we'll return.
If visited of v is true, then we simply return. We don't have to proceed with this function. Okay. Otherwise we push.
Yes.
We mark it visited, and then we check if q is not empty.
So not empty.
Not here. Okay. Tell me what is the code.
No, not empty. Not empty.
Okay. If q is not empty, then
We'll take top element into some temporary variable.
okay. So we take q dot front into temp variable int t.
Then we'll pop.
We'll pop it. So gone from q.
We'll print the what is it?
Print whatever we have taken out. We print it. Then
Then we'll make a recursive call to
all its adjacent nodes.
yes, sir.
So code.
So that
Same for loop we can copy from there and put it here. So when we bring that for loop here, so for this now t we have to change. Previously we took t, we take temp variable, here we change it to v, and in this case we are making a recursive call simply BFS with g, BFS2 with g and t ka data. That is it. BFS2, yeah, this is where we are. So now from main, rather than calling BFS, we call BFS2 and we give the start vertex as 0, or any vertex ideally we can go with. Now when we run this code, okay, BFS2 I have to put in graph.h first. So copy, paste, comma, int v, BFS of 2. So it is infinite loop and then crash. So why it is happening that way, we have to figure out. So let's come here to BFS2. So now you see what is queue and what is visited. Where will they be stored in memory? If we make recursive calls, then call stack frame is created for every call. What is queue here? It's a local variable of the function. When you make a recursive call, you get another queue. Yeah. If you go with recursion, they have to be global. So let's get them. Let's take them here, remove it from here. Now they are global. So with that we proceed. Otherwise what was happening, your queue will never become empty. That's why infinite loop is happening. Reason for crash is every time you are making a recursive call, somewhere the stack space will get full. It is stack overflow which is causing. Now there is no memory for C runtime to create another stack frame. Okay, so now we go with this approach. Okay, here g of nv should not be there. Let's go with 1000 for now, assuming this will suffice. Now we go ahead and give it a run and you got the output, right? So with recursion, if you are going, then yeah, you have to keep in mind that stack frame pe local variables have to be initialized again. Okay, so that winds up BFS. Now we come to, okay, everyone done with BFS? Clear? Rupesh? Sai Krishna? Okay, great. Chalo, now we go with DFS. Yeah, you are talking about DFS? So in DFS, what do? We do depth first search. BFS is breadth first. Breadth means you go breadth wise. 1 level, 2 level. Okay, in depth first, what will happen is, if you look at the slide, if we are starting DFS with 1, that means we first print 1. It's like in tree we did pre-order traversal. We are going in depth. First root printed, then its child, then left child, then left child. So in depth we go, we don't look at the level. So same way, if we start with 1, first 1 will be printed. If we look at here, who is the adjacent of 1? First is 3. From 1 we go to 3. We print 3. From 3 we go to 3's children. So we come to 3. 3 has child as 0. We go to 0 and we print 0. From 0 again we are connected to 4. We go to adjacency list of 0. So from 0 we go to 4. So we never stop. From any node we reach, we go to its first child, then to that first child, another first child. So we have reached 4 now. After 4 we go to the 4th list. 4 is going to 2. So 4 will print. 4 will ask 2 to print itself. After 2 we look at the list of 2. Now 2 is saying my adjacent is 4. Should we come back to 4?
Already visited.
No, it is already visited. So in DFS also we need visited, because every node should be printed only once. So what happens, from 2 we say, oh, 4 is visited, so I should not be asking 4 to do a DFS again. Then if 4 is done, then 2 will go to the second child. What is the second child or second adjacent node of 2? Null. So 2 says all my adjacent are covered, I want to go back and I want to give chance back to where I came from and ask 4, can you proceed with your adjacent vertex? So here 2 is done, so we will say 2 is marked green, that I am done. So it is backtracking again. 2 is saying I am done, go back, start from where you left. So 4 started with 2, now 4 start with 5. 4 made one call with 2 and said, 2 you do recursive DFS, then I will proceed with 5, then I will proceed with next, and then when I am done I will return back to my parent. So now we come to 5. So from 4 we went to 2, we came back. Now from 4 we are going to 5. 5 will be printed. 5's adjacent are 1 and 4. 5 will not ask any of them to make a recursive DFS. Clear? So here recursion is involved. 0 is asking its first child to do a DFS of that. Once it is done, come back, 0 will go with the next child. It will ask next child, do your DFS, come back. So it's similar to in traversals. We are saying one node will ask its left child, you do traversal, then tell me, then you do, then tell me, then I proceed. Okay, so DFS we have to do. Here also first we can write with a vertex, then we'll proceed to solve the problem of connected components. Now we need a visited array here. Okay, now challenge is we have a global visited array. If we declare local also with the same name, what will happen? There is a global visited array and local. Local will be given more preference. And this function though won't even know there is a global visited array, because it is defined after the function. Right? So even if there is a local and global variable, local is given more preference. So fine, first 3 lines we will copy. We need visited array, we need memset. Okay, these 2 lines only. Yeah. Then what we do? In DFS, when we come to a node, do we print it immediately or not? We print it. If it is not visited, then only we print it. So let's remove that check right now. Let's go directly. If we have made a recursive call, we will print it. So we simply say printf %d g of v. So one node is printed in DFS. We reached 1, we printed that. After that, what do? We go to its first child and make a recursive call. We go to second child, make a recursive call. So how do we get to adjacent nodes of this?
Loop over that.
Lel node star t. Yeah, loop over that.
List, sir.
Adjacency list of v. We start with the head t not equal to null, t plus plus, t equal to t next. Typically it becomes our habit to do plus plus, right? For loop whenever we are doing. Okay, then here what we do? We make a DFS call with t of data as data and graph as it is will go. So this is our logic. We print the node and we call recursively for all the adjacent nodes. Now only thing we have to worry about is visited array. Again the challenge comes, visited is on stack. Visited we are defining locally. So it should be global array. So it should either be a global array,
Or
or if we want to keep a local array, we should pass it as a parameter and not declare here. So somebody who is the caller of DFS main, he should be passing the visited array every time to recursive call will be passing it, right? Sanjay, clear what we are talking about?
we can create it to
Global we take, it's easy, right? I know that solution is already clear to you, so this time we'll take a different approach. So what we will do, yeah,
we'll create two functions.
yeah, we will create two functions. Why should we put an overhead on main to create the visited array? Main is our client, consumer of our function. Main should be very lightweight. So main is calling our DFS. DFS will make sure, rather than printing things here, DFS will call a function DFS internal, to which it will pass G and V. And that function is recursive, DFS is not recursive. So we say void DFS internal graph star G int V bool visited. This one will get the visited array and all that logic will put here. So everyone clear on why we are doing this way?
Even in Q also.
Here we don't need Q, DFS. In DFS, so ultimately recursion is giving us the stack. So this way our DFS function is lightweight. It is asking a recursive function to every time pass the visited so that the state of visited is updated. Okay, now the question is, where should we mark visited, where should we check visited? After printing, we mark it is visited because it is done. Visited of V is true, V is done. Then where should we check? Before printing we should check if visited of V is true, don't do anything, this node is done. This is the step of backtracking. One node comes, it says I am visiting, I go back. When all the children of a parent tell him that we are done, this parent goes back because it comes to the end of the function, and this will be our DFS. And most of the graph problems will be based on either DFS or BFS. So data structure related problems, everything will be solved with this. If we say count the number of nodes in the graph or count the connected components in the graph, there is a problem like that. How many components are connected? Then only, I mean, we can use any of these traversals to find out that. So once solve it, then we will take a look at that kind of example also. DFS of G comma 0. Okay, this DFS is taking a vertex. So I am adding two functions of DFS, DFX with start and only DFS, and we will try to reuse that function. So DFS with start is the one that takes a vertex. Normal DFS does not take any vertex. You go to graph.cpp. This is DFX with vertex. We add only DFS. What will only DFS do? It will call DFS with start, or it should call DFS internal. This DFS is to print all the nodes, they are connected or not connected, everything should come like we did BFS.
Means we need
So it will simply be copy of the previous one, just that we are not taking the initial vertex, we are writing a loop and then we are going like that. So this DFS will give us all the vertices. functions. Too many arguments. DFS internal takes visited also. Okay. Ideally we should have done one thing. In BFS we should write it is BFS. In main I can do that. Printf BFS. हो गया. After this I'll give you one exercise, interesting exercise. Okay, so what we will do now is, see, this is one file which has, how do we see, it has 30,000 lines. So till today whosoever attended our workshops, we took everyone's names, put it in a file, wrote a program. If the name is 2-letter word, like if it is Shiva Chaitanya, Shiva we split separate, Chaitanya separate. So Shiva is another guy, Chaitanya is another guy. And then randomly we generated their friendship relationship. So here you can see Tithi and India, they are friends. So every line contains two names, comma separated, and they are friends. What we have to do, we have to write a program which reads this file, and after that it presents a menu to the user. What do you want to do? And the menu will be something like, first choice will be print friends of person. When somebody gives first choice, program will ask, give me the name. So if I say name is Niswarth, then the program should print who all are the friends of this person. Right? So internally, after reading this file, what we have to do? We have to make a graph. Now graph that we are making, that graph is of integers. But here we are getting names. So what we should do so that we can maintain the mapping? So ideally, if we go into this file once, every time we get the names, we can read two names using scanf, right? But there is a comma here, so how do we segregate the comma?
Means while taking input percentages, comma percentages.
Yeah. So in scanf there is a property. If you do scanf %s comma %s, it will make sure it is putting the first string and then comma it is ignoring and second string in the second variable. So you can say name1, name2. That's how we are reading, putting in two variables. After reading these variables, you have to store these variables somewhere in some structure. So what is the best place to store these names? Because later on, when same name comes again, here it is Niswarth and Ashiana. If again Niswarth is there and India is there, then we don't have to insert the name of Niswarth again.
We can maintain math, no sir, means for strings and integers.
Okay.
For Niswarth 0 index, for Ashiana 1 index, and
Okay.
we can use the same graph again.
Good point, which is somebody was saying try. Who said try? Rupesh said. So map is nothing, dictionary we have to maintain. We are saying if Niswarth comes, he will have one key associated with this. Niswarth came at 0th position. Because every time Niswarth comes again, we have to check in the try and ask, was it there earlier? If it was there earlier, tell me the index of that guy. And index is, this index is the vertex number in the graph. So when we get the name, we put it in the try. In try node, we will add one more field, and name of that field will be IDX. We have a boolean is end of word. We have the next pointer. Now we are adding one more field, index. So next time I get Niswarth and Ashiana, I will check, is Niswarth there? If it is there, what is the vertex number of Niswarth? In try, it will be faster to find the vertex number, right? Okay, then Ashiana comes. Niswarth and Ashiana, first we go to try, we ask, is Ashiana there? Try will say it is not there. We will first insert with the index, then we will insert edge between 0 and 5th. Let's say Ashiana came as 5th. We are saying insert edge in the graph between 0 and 5. So our graph API always works at these numbers. Main will take care of whatever name comes, it puts in the try. So main is like it is maintaining try and graph, two things. Every time a name comes, this name comes, it checks it is there in the try or not. If not, insert it, generate a new index. Index we can have a global value. That global value will tell how many names are there in the try as of now. Clear? Okay, so first option, so I'm just giving you an idea. This is kind of, you can say, a C level, good level project for a second year student. You are making social network functionality by using advanced data structure, efficient one. So names we will take. Where did I write the menu option? Second option, what can it be? Printing name of one person, friends of one person. What else can we answer? Mutual friends. How will this be done? We give two names, tell us mutual friends of them. So input here will be two names. We get the name, we go ask try, give me the vertex number of this, main will do that. And ask the second name, give me the vertex number of that. We get two vertices. We write a graph related function saying, I'm giving you two vertices, traverse or on their linked list, and tell me what are the common nodes. So what we get back is another linked list with common nodes. There again it will be vertex number. But we have to print ultimately the names. How do we print the names when we have vertex number? In try. Do we have reverse search in try? In try we can search name to index mapping we can do. But index to name mapping can we do in the try? Because index will be stored in the last node.
Sir, index where will stop, sir, in try?
In the last node. I mean every node will have an index. Initially its value will be -1. In create node will initialize with -1. But whenever you are inserting, you mark isn't a word true, right? There you put index. So now the challenge comes, how do we convert index back into name? So we need some mapping again. Where, what is the good data structure where we give the index, we get the name?
Map.
Map is again this try. Array. Hash table is again, it goes by key value. So these terms that we hear, hash table, map, everything is try. Internally it means that's a dictionary. Map means a map between key and value. That's why they call it map, not dictionary. So we have try for that. But if we need index based thing, given an index, give me the value. Array is, the biggest benefit of array is it provides us random access. We can go to any location, get the data. So we need an array now to print the answers back. For searching and insertion we need try. For processing we need graph. And for printing we need array. These three things together will make this program possible, an efficient one. Then we will take it one more step ahead. Right now our graph is fixed because number of vertices we have to tell in advance. We have to make even that dynamic. That your program you can keep on, here you will give one more option, 0, add friends. You just give two names, add it to the graph. We don't worry about where they are added and all. User of the program gives two friends, print friends of a person, mutual friends.
We can use insert edge function also. Insert edge.
Insert edge. Yeah, before insert edge you need the vertex numbers.
Vertex numbers will calculate using that. We said no, sir.
Try. Yeah. So all that is internal detail, right? Here we are talking about from user perspective. He should just give you names. He should get the names back. He is not worried about you are keeping in array.
Add friends should return nothing.
Add friends will return nothing. It will simply print a message.
Friends added.
Chaitanya, Aditya are friends, like Facebook says, right? Okay. Any other thing we can do in this program?
Am I connected to that person?
So is there a path between me and that person? ठीक है? Our friends. So our friends are connected immediately. Are having mutual friends, we should say.
Are friends connected?
Are having any path. So if I want to know in Facebook, this feature is not there in Facebook. If I want to know, am I connected to Narendra Modi through some channel? If I want to know that, I have a friend who has a friend, he knows Narendra Modi. These kind of questions ideally Facebook can answer. But that feature is not there, right? Only mutual it tells. You see some new photo in the Facebook popping up, you go to that, see mutual friends, oh, he is the friend of that. We all know that, right? We do that quite often, right? Okay. So are having any path, or rather than saying are having any path, we say print path. We give two names, tell me what is the path between them, and there can be more than one path. That was next program. Given source and destination, we have to print the path between them.
Shortest.
Right now it is not shortest. Print path here, this program has three variations. One, you print the first path that you find. That is one variation. Second is print all the paths between one guy and another, because there can be multiple channels from one to another. Third is print the shortest one. So those three variations are of this function, but here we are worrying about printing only one path because that is the starting point. Then we will go to print all the paths, which is again backtracking solution. Then we will print the shortest path. So all those three things we are still having remaining. After that I will say graph data structure wise it is over. Applications wise there are many. We can go and do any applications. Okay, so print path. After that, yeah, unfriend. Okay, unfriend means we are just going into the linked list, deleting one node. Fine, unfriend we can have. Block. Okay. Okay, here we do not have the block facility.
Means we cannot add again.
Yeah, then you have to build the hard-coded checks in the program. Okay. Huh? Yeah, then we have to put all those things in the try, because in try we are storing index. Name will be after traversing, last node will have the index. There we can have one more field. Are you accepting friends or not? You mark it false, insert edge will throw error. This person is not allowing you to accept any call. So backend of social network is like that. Then they create the nice website, just call the functions in the backend. So websites, how do they work? We have a web page, whatever button we click, it makes a call to the server. On server some code runs. That code will be something like what we are writing. Ideally they will have database involved, pictures involved, lot of things will be there. But this is, we can say, a starting point of a social network. Okay. Most social person.
Maximum number of friends.
The person with maximum number of friends. Okay, Akhil. Least social person. क्या अखिल दोनों तरफ से टॉपर हो. Okay, and seventh option we will have is exit. This kind of program, this one problem we will do here because it involves a lot of data structures together, coming together. So that we will solve. Okay, so let's say this is the graph that I showed you, the file with which we want to represent. So we can see Kirti is friend of Sneha and Hemant. Most of them, yeah, they are seniors. Yeah, so this is the problem statement. Then we look at how we solve it. So there was a slide for that. Yeah, so this is the slide that answers that question. Assume the last thing is a try. Not last thing, sorry. Last thing is the graph. The first thing is, so that given any name, we can get the, given any index, we can get the name. इसमें try का भी कहीं नहीं है क्या? Wait, I'll see. Yeah, this is the slide that I was looking for. See, when you give two names and say make these two people friends, in menu there is an option. Take two names, mark them friends. So what you will do is, first thing you will do is you will search in this try and ask first person is at which index, so that you can insert an edge in the graph, because graph will be from 0 to n. You have to call insert edge function in the graph. What does insert edge takes from you? Two vertices. Now we are getting two names. We don't have their vertex number. So one option was, we can go in the array one by one, we can search. Let's say we are making Hemant and Mahipal as friends. Two names you got. So one option is you go in this array, you search Hemant is at index 6, Mahipal is at index 9. So you make one function, get index, which will return you integer, take a name. In array, if you go and search, if array is having 10,000 names, efficiency goes for a toss, right? For that, what we said, we'll keep this thing in duplicate, we'll keep everything in try also. Try, you remember? In try, we put the word, we put is end of word true. That's what is the try that we know. Now in that try, we go to the try node. In node, we add one more field and we call that index. Right? Now wherever isn't of word is marked true, there the index of the person will be there. So when first time we insert Abhinay into try, we'll say Abhinay, his index is 0. So insert in try will take two parameters, word and the index of that word. So first name, whenever it comes, we'll insert in try. You say Abhinay is at 0, Kirti is at 1, Bhargavi at 2. So that is how we form try. No, it's not related. Right now it is not related there. Whenever you get two names, first name you check, it is there in the try or not. Try will say I don't have that. Take a global variable idx which knows how many values are there in the try as of now. It is that index if array is not into picture right now. Okay? So when you are inserting, every time you are doing index plus plus, main is making a call, insert at next index. This much is clear. Now whatever that index is where we are inserting in the try, at same index we put in the array also. Okay. Why that is needed? Let's ignore the array for now. Try is clear why we are putting in the try. What is the purpose try is serving for us? Search. It removes duplicates also. Second time the same name comes, we don't have to insert in the try. Right? So right now if we remove array, picture is clear. We are taking the name, putting in the try, we are getting the index. Now when we say make two people, so this is add person. Whenever we are adding person, we are just inserting in the try at next index. So menu has first option add a person into the try. Clear? Now second option in the menu was add make two people friends. Two names are coming. So what we should do, we have to insert an edge in the graph. We have to get their vertex number. If we go in the try, give the first person name, try will give you the index. If that is not there, try will return -1. Clear? So you get the two vertices, you insert the edge in the try and you are done. Their friendship relationship is established. This is clear? Now the challenge comes when we go and say give me all the friends of Anisha. If that is the question coming from menu, list all the friends of Anisha, what will we do in the code? Find the index of Anisha in the try. That is clear? We go inside the graph data structure and we say
At that index, print the list.
third index, print the list. What will that list print?
Integers.
Only integers.
Instead of integers, we need to print names.
Integers will be printed, but what do we want to be printed? Names. Now try does not give us integer to name mapping. So for that reason we said we don't want to kill the efficiency. Let's bring in an array also. It is duplicate, but it serves the purpose. We can print the names back very quickly. So array need arises from there. So to answer back we need array. To get some value we need try. So that's how this structure is. Sanjay, now it is clear. So all this will be there in the main. Main will have an array, a try, root of try and the graph. Main will be dealing with three data structures. Here it is showing as, okay, this is showing as a 2D array. This is not as a linked list because this is how we get people started. Yeah, ideally this is a try. Let me see if we have the try here. Okay, all these are. Ideally you can see in this picture this 2D array will be replaced by the try photo, and try photo was not looking good, so we replaced it with the array because for explanation that works well. Yeah, so here this friendship graph that we are showing, okay, this is try, sorry, this friendship graph that we are showing, it is not adjacency list, this 2D array, so it should be adjacency list notation. I think we should have replaced it easily. Right now it is 2D array. So try is this. We call it symbol table, we call it map, we call it dictionary, people call it with various names. We can implement with 2D array. Without adjacency list we can do that. This is that representation it is showing. So graph is, again, graph's call is from main angle. If you look at whatever code we have written right now, here does the main know in the backend graph has list or array? Main doesn't know, right? So internally we are using whatever, that's up to us. Main does not worry about all that. Main needs this function. Main wants, you give him a function insert edge, it should be able to insert edge between two nodes. But yeah, only thing main has to ensure is these vertices it is passing, they are within the range from 0 to n. Right now that is the restriction we have put. Reason we did not go with arrays, because when we go with 10,000 members and each person has max 5 friends, how many zeros we are wasting? So that's why we said like array will be wastage, because if we take integer array, then it is per person we are storing 10,000 into size of int, that is the size of pointer also. In linked list only 5 nodes are needed, so that gives us space efficiency. In adjacency list, do we have any benefit over linked list representation? If we go with adjacency matrix for graph versus adjacency list,
You can directly retrieve, sir, instead of searching.
so if we have to tell two people are friends or not, in 2D array it is very easy.
IJ index.
We find the index of first person, index of second person, go to that location and tell answer is yes or no. But in linked list, we have to go to the head of the one node, traverse till we find the second number. So here this guy wins. So if we have a graph where more people are connected to each other, take example of one class. In your college, if you take your class as an example, all the persons in that class, they are the vertices. This graph requires adjacency matrix, because most of the people know each other. But if we talk about a graph at a level of city, Hyderabad city, then adjacency list is better. So depending on situation, we pick the data structures. Okay, ji. So fine, this problem we will start tomorrow. I thought I'll introduce today, we'll get started. Monday, sorry. Monday. Print path, leaving as an exercise for today, not for tomorrow. Huh? No? New Year started? Okay. So if you can give it a try to print the path between any two vertices, that will be good, because that will help you in solving the problem going forward. It's recursion practice also. Ideally I could have given you the solution for this function, but give it a try. Print just one path, the first path that you find, not all the paths, not the shortest path.
And if they are not connected, so means two separate components.
If they are not connected, nothing will be printed. So it is recursive. From the end you have to start. End will tell you.
Means 1, 2 are connected and 3, 4 are not connected. Means they are connected but not connected.
Correct.
So
So there is no path. See, your output will be, if it is 0 to 4, output will be 0 to 1 to 4.
there is no path.
No path, no output, blank. Only these two possibilities, 1, 2.
Destroy graph.
Hmm?
Destroy graph. One more function is there. Destroy graph.
Okay, destroy is simple. Destroy linked list for every node, destroy the graph. I mean, free the linked list, free the thing. I'm not worried much about this. This is like, this is unique, so that's why I was talking about it. ठीक है जी, that's where we stop.